So in this video, I'm going to be doing another curve sketching example, and our function today is f of x equals 2x squared over x squared minus 1. So the first step I like to do is to find the domain of the following function. And notice how any x coordinate can be plugged into the function except 1 and negative 1. That is because if we factor things out in the bottom, like x minus 1 to times x plus 1, notice how if we plug in negative 1 here, the denominator of this becomes 0, and we know that we cannot divide a number by 0. And if we plug in 1, also we get the denominator to be equal to 0, and we know that we cannot divide a number by 0. So our domain includes all numbers except negative 1 and 1. So we can write that as the following: all numbers left of negative 1, 2 but not including negative 1, all the numbers in between negative 1 and 1, and all the numbers right of positive 1. Next step that I like to do is to find all the intercepts of the function, and notice that we have two intercepts. We have an x-intercept and the y-intercept. So the y-intercept occurs when x equals 0. If x equals 0, notice how it's 0 over negative 1. So we get y equals 0. The x-intercept is when y equals 0, in this case y is f of x, so when f of x equals 0, so 0 equals 2x squared over x squared minus 1. If we multiply both sides by x squared minus 1, we get 0 equals 2x squared, and we get x squared equals 0, x equals 0. So our y-intercept is y equals 0, and our x-intercept is also x equals 0. So now, the third step is finding any asymptotes. And the first one we should do is easy. This is the vertical asymptote. And notice, for the vertical asymptote, we always have to focus on the denominator of the function. So let's isolate the denominator, and normally to find the vertical asymptote, we set the denominator equal to 0. So let's set x squared minus 1 equals 0. If we factor stuff out, we get x minus 1 times x plus 1 equals 0. And we get two answers here. X can be either positive 1 or negative 1. So x equals plus or minus 1 are our vertical asymptotes. Our horizontal asymptotes, if we look, notice that the highest powered variable in the numerator is x squared, and the highest powered variable in the denominator is also x squared. Since they're this equal, all we have to do is find the ratio between the coefficients. Notice that the top x squared has a 2 in front of it, and the bottom x squared has a 1 in front of it. So the horizontal asymptote is y equals 2 over 1, or y equals 2. So the fourth step is where calculus kicks in, and remember what we want to do is we want to take the derivative of the function and set that equal to 0 to find the x-coordinates, so that we could use the number line test to determine minimums or maximums or intervals of increase and decrease. So let us take the derivative of f of x first. So f prime x equals, remember this is a quotient rule, so quotient rule states take the derivative of the top, which is 4x, times, keeping the bottom the same, x squared minus 1, minus the derivative of the bottom, which is 2x, times, keeping the top the same, 2x squared, all over the bottom squared, which is x squared minus 1 squared. If we simplify things further, we get x cubed, 4x cubed minus 4x minus 4x cubed all over x squared minus 1 squared. These 4x cubes cancel out, so we get negative 4x over x squared minus 1 squared. Remember now, we want to set this equal to 0 to find the x-coordinate, so we can use a number line test. So let's do negative 4x over x squared minus 1 squared equals 0. And notice that the only x-coordinate at which this equals 0 is x equals 0. Because of x equals 0, the top becomes 0, but the bottom stays as 1. So this equals 0 when x equals 0. But notice from the number line test, we also have to test the points where the function is undefined. And remember that the function is also undefined at x equals 1 and x equals negative 1. So when we do our number line test, we have to include 0, negative 1, and 1. So now what we have to do is we have to test the boundaries left of negative 1, in the middle of 0, negative 1, in the middle of 0 and 1, and right of 1 to determine the sign we get from when we plug in a number in the derivative. So let's take negative 2, and if you plug it in here, notice how the top becomes a positive 8, but the bottom will always stay positive. So it'll be a positive over positive, so this is a positive, and we can draw the line slope going up like that. If you pick a point between negative 1 and 0, for example, let's take like negative 0.5, notice the top becomes positive again. The denominator always stays positive, so it's a positive over positive, so it's another positive. So again, the slopes increase like that. If you take a point in between 0 and 1, notice that the numerator becomes a negative number. Like for example, if you take 0.5, the numerator becomes negative 2, but the bottom will always stay positive, so a negative over a positive is a negative. So draw your symbol and draw a down sloping line. And if you pick a number greater than 1, like 2, if you plug it in here, remember we get 2 times negative 4 is negative 8, over the bottom is always positive, so a negative number over a positive number is always negative. Draw your slopes here. So notice that at 0, left of it is there's a positive slope, and right of it there's a negative slope, so it's increasing from the left side and decreasing on the right side. So 0 would become a critical point. Notice that it makes a mountain. Anytime it makes a mountain, that would be a maximum. So there's a local maximum, local max at 0. So anytime it's plus on the left and minus on the right, that point in the middle would be a local maximum when you do the number line test. So now we can write our intervals of increase and decrease. So we can label this as negative infinity and this is positive infinity. So from negative infinity to negative 1, the function f of x is increasing, since when we plugged in a number between these two values into the derivative, we got a positive value. So its function is increasing here from negative 1 to 0. It is also increasing, since you also got a positive number. From 0 to 1, it is decreasing. From 0 to 1, it is decreasing, since you got a negative number. And from 1 to positive infinity, from 1 to positive infinity, it is also decreasing. So from the first derivative test, we got that 0 is a critical point and a local maximum, and we determined that from negative infinity to negative 1 it's increasing, from negative 1 to 0 it's also increasing, from 0 to 1 it's decreasing, and from 1 to positive infinity it is decreasing. So the fifth step is the concavity test, and remember what we want to do is we want to find the second derivative of the function, so we can solve for the x coordinates at which the second derivative is 0 and find any points of inflection. So we know that the first derivative f of x equals, from the previous part, negative 4x over x squared minus 1 squared. So what we need to do is we need to find the derivative of that. So f double prime x equals, remember this is a quotient rule, so we take the derivative of the top first, negative 4 times, keeping the bottom the same, x squared minus 1 squared, minus the derivative of the bottom, which is, remember, there'd be a chain rule, so the 2 will kick out, 2 times x squared minus 1, remember now you need to multiply by the derivative of the inside, times 2x, remember this whole thing is multiplied by the top function, times negative 4x. Remember, this entire thing is over the bottom squared. So that's x squared minus 1 squared squared. So we can rewrite this as, we keep the negative 4 in front, x squared minus 1 squared minus, this will become a 4x in front of the x squared minus 1 times another negative 4x all over x squared minus 1 to the fourth. This again becomes f double prime x equals, keep the first part, the numerator the same, minus, this becomes negative 4x times 4x is negative 16x squared, x squared minus 1, right? This entire thing over x squared minus 1 to the fourth. So now I'm going to bring this over here and I'm going to simplify it further. Remember, we keep the first term the same because we didn't do anything with it. So negative 4x squared minus 1 squared plus 16x squared times x squared minus 1. This entire thing is over x squared minus 1 to the fourth. Now we can cancel out x squared minus 1. So this would become a 3, this would become a 1, and this would go out. So this equals negative 4 times x squared minus 1 plus 16x squared over x squared minus 1 to the third. Let me erase this bottom part so you don't need it anymore. So that is the second derivative of the function f of x. And remember, we want to find the x coordinates at which the second derivative is equal to 0. So we need to set this equal to 0 so we can find our critical values, any POIs, and our intervals of concavity. So let's set negative 4x squared minus 1 plus 16x squared over x squared minus 1 to the third equal to 0. If you multiply both sides by x squared minus 1 to the third, this will cancel out. So we get negative 4x squared minus 1 plus 16x squared equals 0. We can now bring this coordinate into the brackets, so we get negative 4x squared plus 4 plus 16x squared equals 0. We can add like terms now, and we get 12x squared plus 4 equals 0. X squared equals negative 4 over 12. And notice now that we can't take the square root of a negative number, and thus we get no x coordinates at which the second derivative is 0. However, for the number line test, you still have to test out the two undefined points. So we still have to test x equals 1 and x equals negative 1. So, and if we do that, remember, we put negative 1 over here, and we need to test points left of negative 1, in the middle of negative 1 and 1, and right of 1. So, let's take a point left of negative 1, let's take negative 2, and let's plug it in this function to see whether the number we get out is positive or negative. If we do that, I'll tell you right now, this will become a positive slope. So, draw a positive slope like that. If you plug in 0, you will get a negative number. So any number between negative 1 and 1 will give us a negative number. So we can draw a down-sloping line. And a number greater than 1, I can tell you right now, will give us a positive number. So you get a positive slope like that. And you can test that point if you want to, but you get the exact same results. So notice that at each of these points, left of it and right of it, the sign changes. For example, for negative 1, left of it's positive and right of it's negative. However, we can't say that these two are points of inflection because they're undefined in the function. Since these points are undefined, we can't state that negative 1 and 1 are points of inflection, but what we can state are the intervals of concavity. So we can say that if you label this as negative infinity and this is positive infinity, that from negative infinity to negative 1, it is concave up, since it's a positive sign. From negative 1 to 1, it is concave down, since we got a negative sign. And from 1 to infinity, it is again concave up, since we got a positive sign. So from the concavity test, we notice that there are no POIs, since these 2 points are undefined, and we noted the concavity, the regions of concavity. So from negative infinity to negative 1 is concave up, from negative 1 to 1 is concave down, and from 1 to infinity is concave up. So now that we have all our information, I just thought it would be easier to put it in a table format. So the domain we found was from negative infinity to negative 1, from negative 1 to 1, and from 1 to positive infinity. Our intercepts, we had 2. We had x equals 0 for the x-intercept, and y equals 0 for the y-intercept. We had 3 asymptotes. We had 2 vertical asymptotes, x equals plus or minus 1, and we had 1 horizontal asymptote, at y equals 2. We had a maximum at x equals 0. And we had an interval. We had an increasing interval. So from negative infinity to negative 1, we had an increasing interval. Sorry, increase. From negative 1 to 0, we also had an increasing interval. From 0 to 1, we had a decreasing interval. And from 1 to positive infinity, we also had a decreasing interval. So, for our POIs, we had no POIs, none. And for intervals of concavity, from negative infinity to negative 1, we had concave up. From negative 1 to 1, we had concave down. And from 1 to positive infinity, we had concave up. Remember, concave up means that a function looks like a U shape. Concave down, remember, looks like a mountain. And concave up looks like a U shape again. So now we are actually ready to graph the function. So let's first graph all the asymptotes. So we have 3 asymptotes. 1 at x equals negative 1, so down here. 1 at x equals 1, so over here. And 1 at y equals 2, so over here. Let's do our intercepts. We know that we had an intercept at x equals 0. That means we have one intercept over here. And we had an intercept at y equals 0, which is also at the origin. And we noted that our max was at x equals 0, which means if we plug in 0 for x, we get y is 0. So the max occurs at the origin as well. So now, let's use our intervals of increase and decrease and our intervals of concavity to actually graph this function. So we know from negative infinity to negative 1, our function was increasing, so at an increasing slope, and its concavity was upwards like that, like a U shape. So now the only part of this U-shaped thing that's increasing is this half of it. So we can say that from negative 1 to from negative infinity to 1, the function looks like that. Now, from negative 1 to 0, we noted that the function was also increasing, so it was going like that, but the concavity was downwards, like a mountain shape. So for this, we can say it was going like that, right? It looks like a mountain, half a mountain. From 0 to 1, we noted that the function was actually decreasing, so the slope goes like this, but the concavity was again down, so we can draw this as the other half of the mountain. And we know for 1 to out to infinity, the function was decreasing, and the concavity was also was actually concave up this time. So it's this part of the upward of the U shape. So we can say it looked like that. So there you go. This is the sketch of the function f of x equals 2x squared over x squared minus 1. And all we did was follow the 5 steps that I use, and voila. That's simple. Thank you guys for watching, and please comment and subscribe below.